Yeah,
I should give you the
presentation if you.
because maybe I should send Fabio right? Fabio, but maybe from ground.
Yeah, yes.
But sometimes the phones.
No, PowerPoint works quite well. The problem is you cannot put our presentation.
Okay. So let me. Can you give? I want to take the image of it. Hello.
Make sure that it is connected that I said. Okay, we go to your presentations. Yes?
Yeah, no, it's already on the computer. It's already open.
So, yeah, we need to share. What is it? It's not yet.
You just have to, okay, now you should choose your own.
This one. Brother, is it working online? You can also give it back. Las fórmulas están de las multiplicaciones. La supercortés, los normales, límites. O sea, estamos probando con los distintos, los iguales y un día que son o sea, que los iguales ahí hay la clase en la fórmula. Entonces, es matemática.
Sérgio Tervi, sempre agora.
But he's not, but he's still working. Yes, it's very always involved, even in different time. I also look at
I've never been in England. Shame.
Sí, preguntas.
No, you know, used to collaborate with people in Barcelona. So,
yes.
So we call G, S, J.
No, yes.
Sí, era un correo con dos.
Mandaste antes, sí.
Bueno, me gustaría tenerlo.
Con lo que estoy viendo, se puede comprarse. Para tenerlo ahí.
Una lectura
Claro, es de consulta.
de consulta.
Es Si esto lo vuelvo ya en lo antes. Sí, lo paso.
Como veas.
Si nos llevan a comprarme los 2 días, yo lo hago. Porque sé que me lo.
Está guay,
no quiero quedar.
Presentation one. No, not today. No, it is. It be one problem. Kind of open the presentation one. Presentation not today. If you find the pixel error, it can be problem. And unfortunately, I'm not presenting you with that. No?
Good morning to everyone. Please enter the video. Apparently, today we can start without technical problems. Let's hope. The first speaker today is Simon Mudet. He's a PhD student of the University of Trento, and he's going to speak us about some sort of generalization of the Neanderthal in Metric-Affine spacetime.
Thank you. Good morning. Yeah, so I will, this talk will be about the so-called Near-Young topological term, which was first discovered in the context of Einstein-Kaplan theory, where you have beside curvature also non-metric spacetime, non-metric spacetime torsion present. And I will discuss about the possibility of extending this notion to the case of non-vanishing non-metricity as well. And as a particular example, I will focus on a modified gravity model and report some cosmological solutions in this model. So first of all, I will briefly recall the basic properties of Metric-Affine gravity and the role of projective transformations there. Then I will recall the usual definition of the Near-Young term and discuss its generalization to the case of non-vanishing non-metricity. And as a concrete example, I will show you a particular model featuring this new generalized Near-Young term. And in this model, I will present cosmological bouncing solutions in Bianchi 1 spacetimes and discuss the non-geodesics and scalar perturbation behavior in this kind of solutions, which turn out to be affected by some kind of singularities. So first of all, well, as most of you already know, in Metric-Affine gravity, the connection is considered as an independent variable, and it's not determined only by the metric tensor and its derivatives. So this allows for the presence of torsion and non-metricity, which are defined as the antisymmetric part of the connection and in terms of the covariant derivative of the metric, respectively. So recently it has been shown that projective transformations are important in some kind of Metric-Affine gravity theories. And the projective transformation is simply a shift in the independent connection depending on an arbitrary 1,4 psi. And it has been shown that the breaking of projective symmetry can be related to the dynamical instability in some classes of Metric-Affine gravity. So we will keep in mind this aspect in the following. So let me now recall the usual definition of the Near-Young term, which, as I said, was first discovered in the context of Einstein-Hartmann theory, where only torsion is present, additionally to curvature. So we set non-metricity to 0 in this subclass of theories. And the Nyaya topological environment is defined in this way. So you see there is the totally antisymmetric Levi-Civita tensor. It has a term quadratic in torsion, and then a term featuring the Riemann tensor of the independent connection. So the motivation in studying this kind of term is rooted in the fact that it finds application in several different contexts, such as in loop quantum gravity, in the coupling with spinor fields, also in some parallel models, and even in some systems of condensed matter fields. So, the basic property of this term is that it is a topological term. So you can, starting from this expression, you can show that you can rewrite it in this way, where now the covariant derivative with a bar is simply constructed with the Levi-Civita connection. So the question is, what happens when you relax this condition? So when you allow also non-metricity to be present in the theory. And it turns out that if you try to recover this expression starting from the usual definition, you end up with an additional term on the right-hand side beside the total derivative. And so in presence of non-metricity, the Nyaya term is not a topological term. Now, moreover, if we check the behavior under projective transformations, we see that it is not even projective invariant. So these two properties are lost when non-metricity is taken into account. And if one tries to recover them, one easy way to do it is just to define a new Nyaya term in this way. So simply moving this term on the left-hand side. And in this way, it is, of course, a topological term. But remarkably, it is also projective invariant. Actually, there is a more general way to do this, and it consists in introducing two parameters, lambda 1 and lambda 2, and defining a generalized Nyaya term in this way. So with an additional term in which non-metricity appears explicitly. And now we can see what happens. So in this case, this is the behavior under a projective transformation, and this is how you can rewrite the above expression. So you see that if you set lambda 1 equal to lambda 2 equal to one single parameter lambda, then you recover projective invariance. Despite topologicity is still violated by these additional terms. If you moreover set this lambda equal to 1, then you recover also the topological term. So the projective symmetry is implied by the topologicity, but the reverse is not true. Okay, so of course you can set for specific values of these two parameters, you recover the usual for lambda 1, lambda 2 equal 1, 0, you recover the usual Nyaya term. And if you set both parameters to 0, you recover what is called the Olst term, which is simply given by this contraction of the Riemann tensor. So as I said, the Nyaya term is used in loop quantum gravity, and it is used in order to implement the quantization techniques of loop quantum gravity. And this is done simply adding the Nyaya term to the Einstein-Hilbert action in a metric-affine formalism, coupling it with a constant, which is called the Mirzi parameter beta 0. So it turns out that this parameter is labeled different non-unitary equivalent quantum sectors of the theory, so it is a quantum ambiguity. And in an attempt to solve this issue in literature, an idea was proposed consisting in promoting these in Mirzi parameter to a scalar field, a dynamical scalar field. And this was done applying this substitution by hand in the action and possibly introducing a potential term by hand. While we will see in a while that there is a more natural way to obtain the same result. So we take into account the generalized Nyaya term we define, and we considered as a concrete example a model in which we have a function of two arguments, the generalized Nyaya term and the Ricci scalar, of course, in a metric-affine formalism. So as usual, it is convenient to discuss the theory in the Jordan frame, which is obtained defining these two scalar fields and this potential term, and eventually this is the action in the Jordan frame. So, now we see that we can identify this field beta with the immersive field, and in this way we are able to give to promote the immersive parameter to a dynamical field and also include the potential an interaction term in a more natural way, and without the need of introducing these features in the action by hand. So, so consider this theory, and of course, its dynamical properties will depend on the values of the two parameters inside the definition of the generalized Young term. And this can be seen in particular looking at this specific contraction of the field equations of the connection, which simply yields this condition, where S mu is the axial trace of torsion defined in this way. So you see here that if you consider the case of where projective symmetry is broken, so if lambda 1 is different from lambda 2, then you are compelled to set S mu equals 0. And it turns out that in this case, even if the projective symmetry is broken, there are no instabilities arising. And this is already seen looking at the expression the Young term acquires in this case. And you see that on shell where S is 0, this is 0. Moreover, you can also solve the full set of field equations for the connection and substitute the result back into the action. And you obtain this effective second order theory, which is just Palatini-Jacober theory in the Jordan frame, with the potential depending also on the immersive field. However, of course, the equation for beta simply tells you that beta is a function of phi, and the equation of phi are the usual structural equation of Palatini-Jacober theory. So you see that in vacuum, where T is the trace of the stress energy tensor. So in vacuum, both fields are forced to be a constant, while even in presence of matter, they are not independent dynamical degrees of freedom, and so there are no new instabilities arising due to the presence of these additional scalar degrees of freedom. Regarding the other possibilities, so when you set the projective invariant case, so when you set lambda 1 equal to lambda 2 equal lambda, then the effective theory is given by this action, where we reparameterize the immersive field in terms of new scalar field psi, and we define the potential term. So in this case, the equation for the field phi is modified by this additional term, but it still implies that phi is not an independent dynamical degree of freedom, and it's instead related to psi, its kinetic term, x, and the trace of matter. So while if you compute the equation for the immersive field, it is actually a differential equation. So it is the immersive field is the only additional dynamical degree of freedom. And let me just note briefly, curiosity here, that if you take lambda equal 1 and neglect the potential term for the immersive field, it can be shown that this theory is actually equivalent to the experimental compatible subclass of the general high order scalar tensor theories. As a concrete example, we considered cosmological frameworks, and we derived some bouncing solutions. And in particular, we choose a potential for the field phi, a quadratic potential of this kind, and we focus on Bianchi-1 spacetimes, where you have anisotropic spacetimes, where you have a scale factor, a different scale factor for each spatial direction. We include perfect fluid matter content with the usual equation of states. And so here, if you define the volume-like variable given by the product of the three scale factors, can be shown that the TT component of the metric equations can be rearranged in this way, where we define the Hubble function of the volume here, and it can be shown that this function is just a rational function of the volume V alone. So this allows to determine bounces and turning points determining the positivity intervals of this function, and then the lower and upper bounds will correspond to bounces and turning points respectively. So in this way, we are able to identify some bounces in the volume, and then integrating the field equations, we obtain these solutions where this is the vacuum case, and we have bounces for negative values of the parameter alpha, which are shown here for the volume, and here are the behavior of the scale factors. And so I just want to note that there is a future finite time singularity at some time tc, where the Hubble function diverges. And let's note here that in correspondence to that time, the scale factors are neither vanishing nor singular nor infinite. So this is the vacuum case, and regarding the metric functions, while the scalar fields behave in this way, and you see that asymptotically one recovers. Asymptotically they relax to constant values, so phi goes to 1 and the energy field goes to a constant, and therefore one recovers the usual loop quantum gravity picture where with a constant energy parameter. So the energy field relaxes to a constant value at late times. Now we extended these kind of solutions in the case of in the presence of matter, both in the form of radiation and dust. And it turns out that the solutions are affected both near the bounds and in the asymptotic region. So regarding the latter, while in vacuum, so here you see plotted the degree of anisotropy, which should go to 0 if you want an isotropic universe at late times. And you see that in vacuum this does not happen. The black line goes to a constant, while including both either radiation or dust or both, then you are able to provide an isotropization mechanism for the universe. And the behavior near the bounds is not affected if the parameter alpha is in this range, where alpha bar is given by this value. So in that case, the solutions are qualitatively similar to the previous one, the vacuum ones I've shown you. While in the other range, the solutions are different. And in particular, you still have a bounce in the volume, but there are no singularities in the Hubble function, while the scalar field phi goes to 0 at some time tc. And in correspondence to that time, the scale factors either go to 0 or diverge. So bottom line, we have these two kind of solutions, and there are singularities in both of them. So we studied the behavior of null geodesics and scalar perturbations near these singular points. And so for the null geodesic, it can be shown that they have a first integral in this form, where prime denotes a differentiation with respect to the affine parameter S, and these are all constants. And so you see that potential problems may arise if one of the scale factor goes to 0 at SC in the singularity. So if you assume this behavior, for example, for the scale factor A, it can be shown that you can still have regular geodesics if the parameter gamma is between 0 and 1/2. But you see here that, so this is the dashed black line is our numerical solution. And so you see here that in the case when, of course, this referred to these kind of solutions where you have one scale factor vanishing. In this case, the gamma corresponding to our solution is not in this range. So we are forced to discard the second kind of solutions. While in the first kind, the scale factors are non-vanishing, so the null geodesics are well behaved. And in that case, we can study, therefore, the scalar perturbations, which we decomposed in these normal modes. And it turns out that they have to satisfy this equation, where these are again constants, and this is a regular function of the volume. So now you see that you can have problems due to a divergence in the Hubble function of the volume. However, we managed to solve these equations near the singularity at TC, and it turns out that either in vacuum or in presence of matter, the solution is bounded, so scalar perturbations are bounded, and therefore we conclude that in the first kind of solutions, both null geodesics and scalar perturbations are well behaved, while in the second kind, they're not. And let me end with a final remark that we expect further regularizations of these kind of singularities due to effects, quantum effects of particle creations, which are shown in literature to yield additional terms in the effective terms in the Friedmann equations, which are able to stabilize this kind of singularities. So that's it. Thank you for listening.
We proceed with a question. And some doubts can be answered.
Yes, you mentioned that this is an open question. You are not supposed to know this, but please give me your thoughts, your opinion about it. You say that the Nietzschean term is useful in, or is used in loop quantum gravity. Okay. So, and what is the effect in the framework of loop quantum gravity of that term? What is the role, the relevance of that term?
So the relevance of the usual Nietzschean term is, or of this generalized one, the usual. So, so the role of this term is, so basically loop quantum gravity is based on the idea to recast general relativity in terms of another different set of variables instead of the metric and its conjugate momentum in the Hamiltonian approach. And these variables are called Ashtekar variables. And one way to implement these Ashtekar variables is to add these Nietzschean term in the action. And if you do this and then follow the usual, Hamiltonian approach to quantum gravity, so you perform the ADM splitting, the 3+1 splitting, and compute the Hamiltonian and all the conjugate momentum, then you can show that the Hamiltonian phase space can be described in terms of these new variables, which are, so the main advantage is that in terms of these variables, it is easier to apply some quantization techniques which are borrowed from other non-abelian gauge, the quantization of other non-abelian gauge theories like QCD. So the main reason is just to modify the theory, but only in the quantum level, because of course the usual Nietzschean term is a boundary term, and if beta 0 is a constant, this doesn't affect the classical theory. So this is the aim of the philosophy.
If I understand correctly, that term is not affecting the dynamics, but it's changing the algebra of constraints.
Yes, so it does not affect the classic dynamics, but the constraints are different, and therefore quantum picture.
I mean, if you insert Lagrange field in the theory, something changes, no?
Further fields.
Fermi.
Fermion fields.
Yeah. They come to the axial.
Yes.
Part of the
So you pay additional term interaction for the terms.
Yeah, that's it.
So, and then have you explored in some way the extension of the Nietzschean theory with non-metricity, how it affects the algebra of constraints?
So I don't know about this. I usually, when they do what I've just explained in loop quantum gravity, they assume the metricity condition and then neglect the metricity. I think there are some works in literature where they avoid taking this assumption and study the constraint structure with non-metricity.
Yeah.
But I don't know. So in that case, you should start from an action with this term and see, of course.
I think that the first problems will arise when you try to define the 3+1 splitting and the extrinsic curvature, because the non-metricity, you cannot normalize the vectors in the standard way.
Yeah.
So it's going to be interesting. Okay. Thank you.
Thank you.
Any further questions? Good. I'm just wondering about if you can comment the fourth line. I mean, is generalized.
Okay.
If something changes, if we add coupling also between two non-metricity terms. So
yeah. So yes, of course, this is not the most general choice. You can add, as you said, the quadratic term in the non-metricity, but in that case, you can show that that term contracted with the epsilon just reduces to, just selects the pure tensor part of non-metricity. And regarding these analyses, it turns out that the tensorial part of non-metricity and torsion are vanishing on shell. So these will not affect these classical analysis. Of course, returning to the question by Gonzalo, would be different in the phase space, but not here.
okay, I don't know. Let me check.
Are there questions online?
No.
Okay, thank you.
No.
So let's thank you.
Thank you.
Thank you.
Now, how do we proceed?
The next speaker
It's
is
unveiled, but it's online.
so it's in online, so we have to make the present of the presenter. No, I really have to wait. Okay, open your microphone.
Hi, I'm here.
Okay, now you're a presenter and you can share your screen, or the window that you want to use, and maybe also your video to see if you are still alive. Are you in good health?
Okay.
Be careful.
Hi. Well, okay.
Yeah. So next speaker is University, so here in Valencia. He's going to speak us about boson stars in. Okay.
Sorry, I cannot hear you.
You can start.
Okay. Okay, so hello and good morning to everyone. I would like to be there, but unfortunately I'm a little bit sick. But it's not what you think. It's not COVID. It's just a normal cold. Okay, so here I'm going to introduce a recent work I carried out with my advisor, Gonzalo Olmo, who I think is there.
Don't blame me.
And with Jose Antonio Font from the Department of Astronomy and Astrophysics here in Valencia, and Nico Sanchez, who is right now in the University of Aveiro. Okay, yes, all of you know, since the detection of gravitational waves in September of 2015, there has been opened a new window to astronomical observation. LIGO Virgo so far has observed like 50 signals, I think, more or less, of mergers of really compact and massive objects. This collection of detection is providing us a a lot of crucial information about abundances and mass spectrum of this kind of objects. Observing the collection of data, we can see that observed masses for black holes are significantly larger than the ones observed from electromagnetic observations. Also, we have observed that there are objects that are starting to populate the gap between heavy neutron stars and the small mass black holes. And also, we have observed that in the high mass end, we find an object whose progenitors are located inside the parent stability supernova gap. So all of these things raises a lot of questions about our stellar structure models, stellar evolution models, the binary formation models, and also about the intrinsic nature of these kind of objects. So current observations still cannot rule out the possibility that these mergers are mergers of other kind of objects beyond the black holes. So this is what are called exotic compact objects, or ECOs. And among these ECOs, boson stars play an prominent role. So what is a boson star? Okay, so boson stars are gravitationally bound configurations of bosonic particles coupled to gravity. The particle that is that's playing a role here is described by an oscillating complex scalar field. That these oscillations are inducing an effective pressure that balances gravity. As in white dwarfs, electron degeneracy contrasts balances gravitational collapse, or in neutron stars is the Pauli exclusion principle. Here is the Heisenberg uncertainty principle. What prevents the gravitational collapse? So boson stars comes in a huge range of masses, from atomical masses to astrophysical masses. Since the mass of the boson star depends inversely on the mass of the constituent boson, we need to provide an ultralight boson in order to have a mass of an astronomical mass. So, for example, if we want a boson star of 1 solar mass, we have to provide a boson with a mass of 10 to minus 19 gigaelectron volts, which is kind of small. So these objects are horizonless. They don't have a horizon. This is a huge difference from black holes. And here in the plot that is in the bottom, we can see that it doesn't have a surface. This here I plot the scalar field amplitude with respect to the radius, and as you can see, there is no. It's obviously related to the density, and as you can see, there is not a surface, and also these objects has in the top plots, we can see that the relation of the masses with the central amplitude of the scalar field has a maximum mass, then goes down again. Also, we can see that there's a small range of frequencies that are allowed for this kind of objects. And also we have this spiral behavior that is really typical in this kind of objects. There have been, since boson stars' first works in the 60s, a lot of works about their stability evolution, formation from diluted bosonic clouds, and binaries, rotation mergers, and a lot of tools and software and methods have been developed to describe them. So in this, with the hypothetical existence of FECOS able to reach larger range of densities, it opens a window of opportunities to explore potential modifications of the gravitational sector in the strong field regime. So the absence of horizons also can potentially give us some insights on how to extend Einstein gravity. So FFR theories offer a large of freedom while keeping the equations in a reasonable limits of simplicity. So in this work, we are going to work with this kind of theories. There are two approaches that we can use, the metric one or the metric-affine one. The metric one is known that has some pathologies, nonlinearities of the metric FFR approach. Lagrangian, and this is a dynamical scalar degree of freedom. I think Gonzalo talked about that a little bit yesterday. And we are going to use the Metric-Affine or Palatini FFR gravity. So something really interesting and useful of this kind of approach is that above all, from the computational point of view, is that there exists a correspondence between this kind of theories and GR. So the space of solutions of a modified FFR, metric-affine FFR theory coupled to, in this case, scalar field Lagrangian, it's equivalent to GR coupled to a nonlinear scalar field Lagrangian. Here, as you can see, there exists a relation between two matter sectors, the two matter sectors. So just providing an explicit expressions for the FFR function and an explicit expression for the P matter Lagrangian function, we can translate this problem of FFR gravity to a problem of GR. This is really useful since most of the software it's developed in GR. Also numerical methods. If we wanted to solve this in the FFR frame, in the frame of modified gravity, we will have to develop new numerical methods, new software, and so on. So this is useful because we can use well-known tools, and the only thing that we have to do is just play with nonlinear matter Lagrangian. Here also there exists a conformal relation between matter Lagrangians and also between metrics in the frame of f of r gravity and metric in the frame of Einstein gravity. So we are going to do what I said before. Let's provide an explicit expression for the f of r function. So we are going to use a quadratic f of r function, or also called Starobinsky gravity. So in the f of r frame, we are just asking for a spherically symmetric metric, and Matter-Lagrangian, that it's the one that I said before. This x I'm writing here is just the kinetical part of the Matter-Lagrangian, while the potential here is just the mass of the constituent boson. In the Einstein frame, this will translate, also we'll have a spherical symmetric metric, but now, as I said before, the Matter-Lagrangian will have some non-linearities. Okay, so next thing we have to do is just calculate Einstein equations. So and also use the Klein-Gordon equations to obtain the Einstein-Klein-Gordon system. Here, I'm just showing you these equations because I want you to notice that if we set Xi, the gravitational coupling parameter, equals to 0, we recover the equations that we have for boson starting GR. And also, if you realize higher powers of the amplitudes of the scalar field are always multiplied with this psi, as it is obvious. I want you also to notice that we'll now have some denominators, some fractions, where in the denominator there appears a factor that Xi is not, Xi may be negative, so it can goes to 0, and then we'll have some troubles, let's say, something like that. Okay, now we are more or less, we have presented the problem. It's time to try to solve it. In order to solve it, we have to solve it numerically. We have to rewrite the system, and just, I'm not going into detail here, just I want you to give, I want to give you the receipt I followed. We have to rewrite the system in order to make it well posed. Also rescale it to obtain dimensionless variables. So in this case, we rule out the mass of the constituent boson. So the system, the numerical system, will not depend on the mass of the constituent boson, and also will not depend on the frequency of this boson, since we are reabsorbing the frequency into the metric parameter alpha. Then we have to establish some boundary conditions in the f of r frames and translate them to the Einstein frame. We are asking for regularity at origin and asymptotic flatness. So now, as you can see, we have our system of 4 partial differential equations. We have our 4 boundary conditions, even though 2 of them are some finite number that we don't know. So what we have to do now is to choose a value for gravitational coupling, and then for a desired phi, phi with 0 means the value of the scalar field in the origin. We use a fourth order Runge-Kutta scheme with an adaptive step size, and a shooting method to find the right alpha 0. And more or less, this is what we do. We compute this, and we'll have some results that I'm going to show you now. So, sorry, as we can see, disparities here. I just I just some values for coupling parameter, the gravitational coupling parameter C, that ranges from minus 0.1 to 0.1. In reality, since we are doing a qualitative approach and not quantitative, it doesn't really matter the magnitude of this parameter, and because it's expected to be much smaller. So as we can see, disparities with respect to GR, that is the curve in blue, only arise when the scalar field is high enough. And also, first thing that we can notice is that the existence curves are much shorter than the ones in GR. Here in GR, we don't see the end of the curve, but for f of r curves, we can see it really clearly. Dots are representing the end of the existence of this curve. We cannot compute more solutions farther away. Okay, let's talk a little bit more about the results for the negative coupling. This negative coupling generates a repulsive gravitational component when the scalar field is high enough. So a larger number of particles can be sustained, then larger boson star masses are observed. Also, something that you can notice really easily is that we have lost this characteristic spiral behavior, and that even it starts to be a one-valuated function for the mass frequency relation. The reason that why we can why we cannot compute more solutions from further the dot that I represented is because the conformal factor goes to infinity. As we can see here, I plotted different curves as we are approaching the last available solution, and as you can see, it grows rapidly. In order, also I plotted here the relation between the two the area of the two spheres in both frames. Why I plotted this? Okay, if we take a look, the bottom plot is just a zoom of the top one. We see that near the center, we have a behavior that might be similar to something that we have seen, or it reminds us to something that we have seen in also some scalar field with electromagnetic field also in f of r series. And this is just because in other works, we have seen that wormholes may arise in this kind of situations. Even though we don't have wormholes, it's like it wants to do something like that, but our computational methods doesn't allow us to do so. In the for the positive coupling solutions, we have the opposite than before. Now the positive coupling contributes to gravitational attraction, and so less mass can be supported by the star. We see that curves follow more or less the same trend as in GR, but in this case the spiral is tighter. And also there is a direct relation with the magnitude of the coupling. In this case, we cannot obtain more solutions since the conformal factor goes to 0. It's the opposite case as before. And also we have this two-sphere relation that that it's showing us also something similar as before. Sorry. So since Boson stars doesn't have a definite surface, we are calculating its radius by the radius of the sphere that contains an 89% of the mass of the boson star. We can see, and we said before, only for high amplitudes of the scalar field, we have deviations from GR. While in the positive coupling case, curve follows the same trend as in GR. For the negative case, it is not. Curve, the mass function reaches a local minimum and then grows again. That implies that its compactness, that is plotted in the right plot, is monotonically growing function of the central field amplitude, and we can see that it seems like it's diverging. We also explore self-interacting boson stars. We introduce a self-interacting term in the potential, and as we can see easily, increasing self-interaction parameter lambda results in a more massive boson star. For f of r theories, the existence curve shortens as the self-interaction parameter increases. So if you see for the negative coupling and just lambda equals 10, the disparity with GR is hardly noticeable, and for lambda equals 100, the existence curve of these negative coupling parameters f of r theories lays over completely the GR curve. So in order to finish, to sum up, using the correspondence between f of r gravity and GR, it's possible, and to modify we have used the correspondence, and it is possible to turn a modified gravity theory into a modified matter theory coupled to a standard GR. Also, we have proved the existence of boson stars in Palatini quadratic f of r gravity. Shorter range of scalar field amplitudes allowed at the center of the star, and new features arise in the negative coupling case. There is no spiral behavior for the mass frequency relation, and don't forget that these results are valid for quadratic Palatini f of r gravity boson stars, and also for GR coupled to unconventional matter Lagrangian. So we can see it from both perspectives. Solutions do not differ significantly from those of GR and depend on the magnitude of Xi, and they are indistinguishable for small phi 0. There is a high degeneracy between f of r boson stars and GR coupled to exotic matter, and this degeneracy gets worse when we add some self-interactions. And finally, the formation relation between the areas of the f of r and GR frames reminds the behavior of wormholes. This is something that further work has to be done to shine a light on this topic. So thank you. This is all, and thank you for listening. If there is any question.
We see. Okay, please.
Can you hear me, Andrea?
Yes, more or less.
Okay, thank you for your talk. I wanted to know a little bit more about what kind of scalar field or what restrictions do you need to build these boson stars? For example, is it a zero spin field or one spin field?
Okay, the one that I have used is an spin zero field. It doesn't have any spin. This is also just a toy model, but there are also boson stars with the spin equal 1 field. They are called Proca stars. Also, in the last slide I showed you, this one. This is the detection of a gravitational wave that perhaps maybe it may be the detection of the first head-on collision of two Proca stars. So yeah, we have used the spin 01, but there is a lot of confidence with Proca stars and the other objects with a spin different to 0. I don't know if I answered your question.
I have also another question. It was not clear for me if you can build these boson stars with just general relativity, or you also, I mean, you need to include other terms to general relativity to build these boson stars. It may seem a silly question, but it was not clear.
No. These boson stars, you can build boson stars in GR. The thing is that what we have done is that we have translated a boson star in the f of r gravity to general relativity with a boson star plus something nonlinear, and this is our result. But you can have boson stars in GR, of course.
Okay, thank you.
Please. Oh.
Andrea, can you read me?
Yeah.
Thanks for your talk. I wanted to ask, have you considered the scalar field as a classical field?
Sorry?
Have you considered the scalar field as a classical field, not a quantum field?
Well, yes, I consider it as a classical field, but anyway, I'm not into the particle physics. I'm not in the small longitudes physics. I'm just providing a matter Lagrangian and seeing what happens in the astrophysical scenario.
Thanks.
Okay. Please, Florencia, if you...
Yes. Thanks. Very nice talk. I would like to ask about the stability of these configurations, and if you can put some constraints on the gravitational coupling through stability considerations.
Okay, this is a work in progress. Yes, we are using numerical relativity tools in order to study the temporal evolution and the time evolution of these objects in order to study their stability. And as happens in GR, there are different configurations. Some are stable, some are unstable. Since the point of view of the matter, not from the point of view if the theory allows it. and it's just a work in progress right now. But yes, we are looking forward for that.
Okay. Thanks.
That's again our speaker. We proceed further. Our next speaker is Jared already active.
Yeah. Seven or 86.
It's you.
Yes, more than 100. 160.
It's full of energies, no?
Yeah.
Okay.
It's an old computer. Now it's everything crashes. Not enough RAM memory.
It's not a theoretical presentation for sure.
No, animation. You don't see much equations. Thank you. Okay, be patient because this file is full of movies and animations. It takes a while to upload. Y comparte la pantalla. No que se vaya viendo. Yeah, okay. So, you know, if we don't have technical problems, you create them.
I just say that.
We are confident that at some point the computer. No, it's progressing. It's now 89. It is but it's like having a heavy load, you know. Going back again. Listen. Oh, it's okay.
Se acabó, ¿no?
Okay, it's good because I think you have to send it this email. No. Check it.
No, okay. This works.
Maybe I can reshare us.
No, yesterday we had the same problem with your. Oh, no.
A ver si cambia, si puede.
Sí, sí, cambia.
Sí. Sí, like it was.
Does this work?
Sí.
Images for finding the video.
Sí, ya está. No, bueno, pero el teléfono podrá descargar.
No, pero.
I think this is enough. Okay, you can see it and everything will work. Okay, so if you think you can.
Does this work, huh?
Well, no, not that way. I don't think so. Probably you need to use the.
You can get it out.
Yeah.
No problem. So this morning I said we had no technical problems. So. Directions. The speaker is Jared already. He's from Norway. He's visiting us this week. He's teaching us about
Thank you for organizers for this opportunity, and a special thank for Alvaro and Gonzalo to include me to this fantastic Cape Town Valencia workshop and collaboration possible in the future. So I'm gonna talk about my paper that is gonna be submitted soon. It's about BW190521, first measurement of estimated Hawking radiation from black holes. So let's go to detail of that. So first I will give why we are doing this, why we want to measure Hawking radiation and what is the motivation from theoretical side. Black holes are perfect lab for new physics. We have Hawking radiation from black hole, which is outgoing radiation. So this is something that is completely quantum mechanical. We don't have such a thing in GR. But this is a small effect because it comes from vacuum fluctuations, and these fluctuations have H bar behind this vacuum excitation of a stress tensor. So it is very small effect, and we don't expect to be able to measure for this from black hole. But there are something interesting things that can happen. One interesting thing is that we have quadrant black hole mergers that are observed by LIGO window detectors, and their frequency is same as what frequency we expect from temperature of Hawking radiation. So we have for example, for GW190521, there is a 9 solar mass energy that goes to infinity, and the same amount of energy goes and absorbed by black hole. So we are emitting this huge amount of energy to the regime that we don't know what's going on there. Because when these waves go to near the horizon, they get blue shifted, and in GR we know that they can blue shifted to infinite very small wavelengths. But in quantum mechanics, we know that the minimum possible of wavelength is minimum possible length is Planckian. So when the wave is shrinked to the minimum length, what is going on? We don't know. We have Planckian problem. We have possible. We may have possible fireball. We have false wall. So we have gravitars. So they are. They may have new physics there, but from the point of view of Hawking radiation, this is interesting experiment. In another way, we want to know if these waves that go into the near the horizon would they excite a possible quantum states of black hole. So, the rough estimation, we know that if we agree on Wittgenstein-Hawking entropy, we know that the number of quantum states of a black hole is proportional to the square of the mass. So we want to know what energies we require to excite these states. It is enough to divide the total mass of the black hole by this number of states, and interestingly, it becomes same as temperature of Hawking radiation. So these waves can excite these quantum states of black hole. So when a state is excited, it can go again collapse and again emit the same amount of radiation. So we may have some outgoing radiation from this. We may stimulate the Hawking radiation by gravitational wave and get some outgoing radiation. So this is the reason we are interested to look at that. So people have proposed a model for that. So in the near horizon, we have from tunneling point of view, we have a particle can tunnel through the black hole horizon with this rate shown in this equation. This is same as Boltzmann factor in the Hawking radiation. And Oshita et al. Suggested a model that if we could have a reflection from the horizon by this rate, we could have a waveform. Then they suggested a waveform for post-merger echoes, and then we use this waveform to do the search and the gravitational wave. So as I said, the Planck length, which is 10 to the power minus 35, is minimum possible length in the quantum mechanics, but it is not zero. So when it is not zero, the waves that go to the horizon, they don't. We don't need to wait infinite time to see new physics there. For example, for 300 solar mass black hole, these waves can, if they are reflected back, it takes 1 second, around 1 second to see signatures of new physics from 300 solar mass black hole. So yeah. So in classical GR, we have, so I said that there might be a new physics in this region, but we have an angular momentum barrier here. So we have gravitational waves around the outside of black hole that is formed from two progenitors and observed by LIGO. And these waves can leak out in each process of reflection from angular momentum barrier and make successive echoes. So if you plot them in time domain, we see these chain of echoes. If you plot them in frequency domain, we see them as a resonance harmonics that you see in this plot. I use two softwares that is developed by gravitational people in gravitational wave community, and they are open source softwares to look for gravitational waves. i-COOP is the software used to based on template-based search, and CWB is a software based on model agnostic search. So it only looks at coherent excess of energy in 2D detectors or 3D detectors. So we used both of them to cross-validate our search. In our first paper, that is published from 2017, we claim that we found signatures of echoes on the 2.5 sigma evidence. Interestingly, after 2 years, collaboration by LIGO and outside LIGO, they using CWB, they found signals that we were claiming for in the same time delays that we claim on our paper. This is TW 150914. And this is TW 151012. This shows the larger signal. We use i-COOP to search again for echoes in this model, but we didn't find significant signals, only moderate evidence, not very loud. So maybe we are using a non-physical model, or maybe it is a noise feature. So maybe we should use a better model. So we use, as I said, Oshita ETR waveform to search for post-merger signal. So this is Boxing Day event. This also shows, based on those paper, this also shows signal. And we did search for two events, and we didn't find significant signal. Only GW17 or 729 shows preference for echoes. So we also searched, we had also paper, we searched for BNS measurement, because this can be a collapse to a black hole, and we looked for post-merger echo signals for this, and we also found a signal inside the prior range with 4 sigma significance. And we have also get some confirmation based on electromagnetic observations that they have also claimed that this BNS merger must have collapsed after 1 second. And interestingly, the time that they are claiming is the same as the same time that we are finding the signal. But this is something interesting to study more. But I should say that different groups have looked for echoes, and not all of them found echoes. Almost half of them didn't find echoes, or negative results. Other half either found mixed results or positive results. So it's not always the search goes to positive results. And there is a paper by LIGO that they also found no significant signals in PVH measures. But however, I should say that they have used a wide prior range. For example, the delta T echo for example, the amplitude of the prior is as low as the amplitude of the main event, and delta T echo is fixed for all of them, but we know that it can change for different events based on the mass and the spin. And they also have missed DW190521 because it has delta T echo of around 1 second, but it is outside the prior. So let me skip this. Let me go to main search. DW190521, which is the most massive and energetic black hole merger have been observed up to date. And it has 9 solar mass gravitational waves are radiated to outside, and 9 solar mass around same energy is absorbed by final black hole. So it is an interesting laboratory to see whether this amount of energy stimulates the Hawking radiation. So it is a 142 solar mass final black hole. So as I said, we use a Oshita ETL waveform. So if I plot that, it is like this. We have the main event and we have successive echoes. So I did a parameter estimation based on RCBC for them, and I was finding preference for stimulated Hawking radiation or echo with base factor of 7 for this event. And we also did search based on whether the Planck length maybe is not our highest possible or lowest possible length. Maybe we have different scale of energy. So we vary the Planck length by, let me go back to inside this region. It is wide enough region, and but it doesn't change the time delay of echoes very much, only plus minus 20%. But it is something interesting to look at, and we found that the data more prepares super Planckian, but there is, I mean, if you plot them, it's just a slight preference. So, and we found that there is a there is a bit degeneracy between final mass and the Planckian assumption, and there is uncertainty in the final mass estimation based on different waveform and different prior range. So, so we just claim that there is this degeneracy, and this can be studied later. Our student, Luis Philippe Longo, has done extensive study on this student with using CWB software, and he's finding this post-merger signal exactly at the same time that is predicted by model, and so if you reconstruct the CWB waveform and plot the RCBC waveform, they are matching together. So the blue curve is the CWB post-merger signal, and the orange one is the RCBC waveform. So, so if I plot the most likelihood RCBC waveform in time frequency plot as a contour, we have this as main event. We have first echo and second echo. If we have only GR, only we have this part, nothing else. We looked at that with CWB and found what we expect from CWB, the main event, as well as RCBC. We have we used a Boson echo waveform here. So let's do the search for with CWB, and we found that with CWB, they are consistent with each other. I did a cross correlation of two detectors and see what we are looking at. So here you see that what we are looking, first echo is there, and then second echo not showing up in the CW, but we are seeing that in the CW the cross correlation is showing up at excess of pixel. So if we plot the frequency, then in the plot the waveform in the frequency domain, we have and the data. If we have the background here, the orange, the brown curve that it is not oscillating is from GR, expectation from GR. The green curve is what we had as most likelihood waveform from RCDC. You see that it is highly oscillating because we have echo, and the echo are repeating and producing harmonic resonance in the frequency domain. If we plot reconstructed waveform from CWB, we see these features here. You see that it is oscillating as well. Yeah. And another thing is here we have 1D plots. The top 1D plot is expectation predicted from GR, I mean the main event. What time delays we should look for first echo, and you see that it is consistent with the signal. And the frequency plot is the expectation from stimulated half-field radiation, that what frequencies we should look, and this is the expected in expected region. And the energy of echo is around 10% based on different estimation. It can a little bit vary. So to conclude, although no clear and widely accepted observational signs of echoes or deviation from vacuum GR have been observed in gravitational wave detectors today, we might be close. The fact that independent methods find similar signals suggests that echoes should be prime targets for the next generation of gravitational wave detectors. DW190521, which is the most massive event observed today, has a large echo signal. We also argue that previous searches by LIGO-WIGO collaboration have missed this signal from DW190521 due to unphysical prior range, because the physical range is 1 second plus minus 0.3, and they just use this 0.05 second and 0.5 second prior, so it's missing. So thank you.
Questions? Yes, I have some doubts because some things I didn't understand. So you mentioned that there are groups that find the echoes and others don't see the echoes.
Yes.
And you are in the set that sees the echoes.
Yeah.
So how dependent is this detection on this modified waveform profile with the Boson function? Does it depend on that, or is
so this is the first stage that is done based on Boson factor. So let me show the plot. So the Boson factor predicts that this here we have. So this is black hole horizon frequency. So other groups didn't look at this. So if you don't look at this, you miss that. So it is the reason. So the more physical you make model more physical, maybe you find that, and we are not finding that in all of them. But this is the most massive event, so this is interesting. And our first observation, looking at the CWB, we see that this frequency of we are observing, but with our first non-physical model is also showing this field feature in the same frequency. Maybe this is interesting. So yeah, so I shall say that now all of them showing echo. So the significant echo, and we see that if the amplitude of echo is bigger than 0.3 compared to the main event, we can see that using these tools. But if it is less than that, we don't see it. And so there is maybe some physical conditions, playing rule. So we put this as next generation detectors to search. It is interesting thing to search for next generation detectors because they are more sensitive, or maybe wait to see something like 1905 going on. So,
I see. And then if you consider a different Boltzmann factor, a different modified waveform, ad hoc,
yeah.
How the relation would be compatible with this? It would be different.
So it depends. So if it covers this frequency range, it can detect, but with different, maybe the different base factor, different p-value. So the significant change. If you look for loud echo, you may not find, because if you increase the amplitude, expected amplitude of, so let me plot here. We choose the amplitude between here inside this range, okay, to search for echoes. If you look for like you look for same amplitude as main event, you don't see that. So if there is something, we would see easily with like that. We would see that in a spectrogram. Simply look at the waveform, you will see that.
Thank you.
Please.
I've got a very nice talk, by the way. I've got a very naive, sincere question. Any guess about who is the fellow provoking the echo according to the signals you get? In one of your first slides, right, there was this children-friendly image showing that we should have a black hole giving rise to the echoes, right?
Yeah.
What information did you guys obtain from the echo signals that could help us to reconstruct features on the mirror creating the echoes, right?
Okay. So I should say that it is not a perfect mirror. It is not a perfect mirror because not all of them showing that. If it was perfect mirror, we would see in all of them. And it is frequency dependent, but we don't know. We want to explore. Really, we want to explore what is the physics behind that, and to give a condition for that. And we found we didn't find in all of them, just in O1 and this event showing good signal. So with one detection or a few detection, we cannot say more. We cannot dig more on that. If we had more, clear, say 5 sigma, we could dig more on that and extract parameters clearly. But it is, some people say, some people can stop on firewall, but I'm saying that no need firewall, just we have already Hawking radiation that is quantum mechanical and coming from the black hole. So this is some, and we are, for example, non-solar mass energy going. We are in a laboratory that we are emitting non-solar mass energy towards the horizon. What is happening there? Then these waves blue shifted. We know that it cannot blue shift it to 0. There is a length that we don't know about that Planck length, and so it is something that we should look at.
Anyone else? So let's thank again the speaker. Now, Silvia, can you hear me?
Yes, can you hear me?
Now,
Can you hear and see me? I see myself, so.
We see you, we see you.
Okay, so I have to share the full screen, right? So you are seeing my screen. Okay, wait. Do you see my slides?
Oh.
Yes.
Okay. So should I start?
Okay, let's introduce.
I cannot hear you, Flavio.
Wait.
Okay.
Tolto già. Cosa ho tolto?
Guarda un muñequito de arriba y clica la gente.
¿Dónde?
No,
Aquí.
muñequito, ahí. A la derecha. Activa el modo de gravity. Modo de gravity. Tú vas a darle.
Ahora.
Si quieres, se lo vas a hacer. Si le das a ella, no la vemos a ella y le vamos a
¿Así?
Bien.
Mejor? Vale. So the last speaker of today is Silvia Garcia. He is at university. Now is currently doing a PhD in England. She is going to speak us about some aspects of globalization, backgrounds in technology. So when you want, you can start.
Okay, so thank you for the introduction, Flavio. Today I'm going to talk about the research I'm doing here in Sheffield. I'm here to visit Elizabeth Winstanley. I'm in a visit of 3 months, and we are doing some research regarding renormalization of charge scalar fields in cosmological backgrounds. So this will be my talk today. So in Valencia, we have some expertise in one particular method that we can use to renormalize physical observables in cosmological backgrounds, which is the adiabatic regularization method. And here in the group in Sheffield, they are familiarized with the Hanama renormalization method, which is a method that is widely used in black hole physics. So what I'm doing here together with Elizabeth is to see the correspondence, if there is, between these two renormalization methods. So what I'm going to do today is to explain I'm going to give you some introduction about quantum field theory in cosmological backgrounds, and then I will introduce these two methods. And finally, I will try to show you the equivalence or the similarities between these two methods, okay? And then I will give some summary and some conclusions. So, first of all, we work in the quantum field theory in curved spacetime, which is a semi-classical theory. This is semi-classical because for us, the gravitational field is a classical background field, which is not quantized. And what we study is the propagation of matter fields, which are quantized. Okay, so in particular, we are going to focus in scalar fields, scalar quantized fields. So we can say that quantum field theory in curved spacetimes is an extension of quantum field theory in Minkowski spacetimes, and that local quantities are easily extended from flat spacetimes to curved spacetime. Like, for example, the equations of motion is basically the same that we do when we jump from Minkowski to general relativity. However, as you may already know, there are some global concepts in quantum field theory that are not so easily translated to quantum field theory in Minkowski in curved spacetimes, and this will give us some interesting phenomena in curved spacetimes, like particle creation. But I'm not going to talk about this today. So one other particularity of quantum field theory in curved spacetime is that when we compute the vacuum expectation value of any quadratic operator of the quantum fields, we find that this vacuum expectation value is ultraviolet divergent. And we also find that we have more divergences than the divergences that we have in Minkowski. So normal ordering is not enough, and we need advanced renormalization techniques to find the meaningful physical finite quantities. Okay, So now I'm going to introduce the basis of quantum field theory in cosmological backgrounds, and then I will talk about these renormalization methods. So consider a free quantized scalar field propagating in a Friedmann-Robinson-Walker universe. It satisfies the Klein-Gordon equation that you see one, and I want to recall here that we work in the Heisenberg picture, which means that all the dynamics, all the time dependence is carried out by the quantum operators, by the quantum fields, and the quantum states are not dynamical. They do not evolve with time, okay? So because the symmetries of our spacetimes, we can rewrite the solution of equation 1 in terms of orthogonal solutions. We can make a mode expansion because we have this homogeneity here, and we can rewrite the solution of 1 in terms of these nicer functions. Okay, so here we have the creation and annihilation operators. Here we have the spatial dependence, which is the plane wave because of the homogeneity. And then we have this unknown function h that captures all the time dependence of the scalar field. And it is easy to prove that this mode function satisfies this ordinary differential equation and depends, of course, on the background. Depending on the cosmological background, we will have one solution on another. Here we have this omega, which is the physical frequency of the scalar field, and this factor that I'm not writing explicitly, which is a function which depends on the background. It's a function of these derivatives here, okay? And can be interpreted as the natural frequency of the spacetime. And as always, we define the vacuum state by this relation here. Okay, so when we have the mode expansion of the field, we can easily compute the vacuum exclusion value of relevant physical operators. This is the simplest thing that you can do in quantum field theory in curved spacetimes. So we are going to focus on the two-point function because it can tell us a lot about physics, and it is the simplest one. So from the mode expansion, we can easily compute this vacuum expectation value, and we find this function here in terms of the mode, and we have this integral here. It's something easy to treat in some sense. It's not difficult to check that this quantity 3 is ultraviolet divergent, so we have to be able to identify the ultraviolet divergences, and then we have to be able to subtract them to obtain a physical and meaningful quantity. For example, in Minkowski, where we have this value for the mode function, it is not difficult to check that we have a quadratic divergency and then a logarithmic divergency in 4 dimensions. In curved spacetime, as I said, we have more. And we have to be able to, first to identify the ultraviolet terms, and then we have to be able to eliminate them to find this finite result. Okay, so the advantage that we have in cosmological backgrounds is that we can build one thing that is called the adiabatic expansion of the mode function H. Okay, and the advantage of this expansion is that it allows us to identify the expected ultraviolet divergences of the quantum operators. I'm going to explain now what is the adiabatic expansion, and then I will show you how this expansion captures the ultraviolet divergences. Okay, so for scalar fields, this adiabatic expansion is based on this WKB ansatz, where we say that this W function can be expanded in terms of these coefficients omega. It admits an adiabatic expansion, okay? So how do we build this adiabatic expansion? The key point is define correctly the leading order, which naturally, it is very easy to see that the most natural choice is to say that the leading order has to be the physical frequency. And then once we have this leading order, we can construct or we can find the next to leading order by iteration from the mode equation. And just a thing that I want to comment is that we have to assign an adiabatic order to the background functions that we have. In this case, this choice of the leading order implies that the scale factor is an adiabatic function of order 0. The first derivative is of order 1. The second derivative or 2 derivatives is of order 2. So every time we add a time derivative, we are increasing in 1 the adiabatic order of the function, okay, of a given function, okay. So once we have the adiabatic expansion of the mode function, we can perform the adiabatic expansion of the observable we want. For example, for the two-point function, we find this adiabatic expansion. And then once we have the adiabatic expansion, we can look at the large momentum behavior to see if we are able to capture or to isolate the ultraviolet divergences. Okay, so when we do this, we have the following, the following result in 9, 10, and 11. Okay, if we look at the leading order, we see that the first term is going to give us a quadratic divergency when we plug this into the mode expansion of the 2-point function. And then if we look this term, this is going to give us a logarithmic divergency. This is the leading order. So when we jump to the next to leading order, we only find the logarithmic divergency. And then when we jump to the fourth adiabatic order, we see that we don't have any divergency for the spectrum of the 2-point function. So what we say, what we claim, is that the adiabatic expansion is able to capture in its leading orders all the potential divergences of the physical observable, okay? This leading order is like the Minkowski-like divergency, okay, the Minkowski-like divergency, and then this next to leading order is related, this is this extra divergency that arises because of the curvature of, because the space-time is not trivial, okay? Okay, so since with the adiabatic expansion, we can capture the potential ultraviolet divergences, this adiabatic expansion can be used to renormalize physical observables. Okay, so I think you can imagine how it works, okay? The adiabatic regularization method consists on eliminate or subtract to the formal vacuum expectation value of a physical observable the first adiabatic orders to eliminate the ultraviolet divergences and then to end up with a finite result. So what we have to do is first to make the adiabatic expansion of the mode, then compute the spectrum as we did before, and then subtract the first adiabatic orders. In this case, for the 2-point function, we only had to subtract the leading order and then next to leading order. And if our vacuum is acceptable, which means that if this function is, if we choose a suitable initial condition for these functions, then our observable will be regularized, renormalized. Okay, and one important thing that I want to note here is that when we do this adiabatic expansion and adiabatic subtractions, we have to subtract the full adiabatic order, not only the divergent terms that we see here, but the full adiabatic order, the full 0 and the full 2. And this is important because in this case, we have a procedure which is compatible with general covariance. So to summarize some tips about the adiabatic globalization method, it methods respects general covariance, it works in the momentum space, which means inside the integral sign. Then the number of subtractions that we have to do depends on the scaling dimension of the observable. We have seen that for the 2-point function, we only need to subtract the 0 and the second adiabatic order, but if we do the same for the stress energy tensor, we will find that we also have to subtract the fourth adiabatic order. Then this method is a bit limited because it only works in homogeneous and time-dependent backgrounds. This method is unique in the sense that once we define the leading order, we find an ambiguous subtractions that we have to perform. It is what it is. And then it's not minimal in the sense that, as I said, we have to subtract the full adiabatic order, not only the divergent part. Okay, so for some people, this adiabatic method is a second-class method, okay, in the sense that it's very particular for cosmological backgrounds, is not manifestly covariant. So for some people, this is valid only by accident. So what I'm doing here is to try to make connections between this method and another more general method to give some more consistency to the adiabatic globalization method. Okay, so in general, when we forget about cosmological backgrounds and we think about general spacetimes, the usual renormalization methods that they use are called point splitting regularization methods. Okay, what they do is to compute the vacuum expectation value of quantum observables at splitted points, at separated points. And then they realize that when they do this splitting, the vacuum expectation value of these observables is finite, okay? And they realize that the divergences appear when they put the points together, so for short distances. And they also find that these divergences that appear, these divergent terms, are purely geometric. They don't depend on the choice of the quantum state, okay? So what they do to perform renormalization is to split the points, to identify the divergences, to eliminate these divergences, and then once eliminated, they put the points together, okay? And here in this scheme, in this framework, the main object is usually the Feynman-Green's function, which is this object that you see here. And then from this object, they compute all the vacuum expectation values that they need, okay? So to be able to compare this adiabatic regularization method with these general techniques, we have to be able to split the points in adiabatic. That's what I'm going to do. Okay, so what we are going to do now is to compare this adiabatic regularization prescription with a particular point splitting method, which is the Hanama renormalization method. And I'm going to do some changes. So you may ask me why. This is because this is what I'm doing here. I found more interesting to talk about the divergences only for gravitational backgrounds, but now what I'm going to do is I'm going to work in two-dimensional spacetimes because it's easier, and then I'm going to consider charge scalar fields, and I'm going to include an electromagnetic background, okay? So this is the changes that I'm going to do. 2 dimensions, charge scalar fields, and electromagnetic backgrounds. And then if we prove the consistency of the adiabatic method for electromagnetic and gravitational backgrounds, it will be better than only with gravitational background. Okay, and other thing is that because of the nature of the adiabatic method, this point splitting that we have to do, we are going to do it only in the spatial part, okay? So we are going to consider a spatial point splitting. Okay, so let me review in 1 minute the changes that we have to do when we consider charge scalar fields and electromagnetic backgrounds. So consider again a charge scalar field, now in 2 dimensions, in a cosmological universe, interacting with a classical time-dependent electric field described by the potential vector. Now the Klein-Gordon equation that it has to satisfy is 16, and we still have spatial homogeneity, so we can do the mode expansion of the field. Some differences like that here we have two sets of creation and annihilation operators, and if we look at the mode function, we see this minus sign here, but apart from this, is the same, that only with the gravitational background. Now, if we look at the mode equation that has to satisfy H, we find this equation here, which is very similar to the gravitational one, but here we have these 2 extra terms due to the interaction with the electromagnetic background. And again, we can compute, as we did with the pure gravitational case, the 2-point function. Now we have to include this dagger term because we are working with complex scalars, but as you can see here, it's the same expression. Okay, it is also interesting to mention that when we have this electromagnetic background apart from the gravitational, we can also do this adiabatic expansion exactly equal than before, and then we can use the adiabatic globalization method. And again, the crucial point of the method is to define the leading order, as we do here. And I want to mention one subtlety here, that is because of the fact that we have now 2 backgrounds, we have the electric background and the scale factor, we have to establish a hierarchy between these 2 fields to make the method consistent, okay? So this is a technicality. We have to consider this scale factor of adiabatic order 0, and this potential vector has to be considered of adiabatic order 1 to make the method consistent. Okay, but forget about them. As before, once we have the adiabatic expansion of the mode function, we can compute the adiabatic expansion of the 2-point function, like you can see in 20, as we did before with the gravitational case. And just, I have written here the leading order terms, okay? So what we have to do now is to make the same computation, but splitting the points, okay, to be able to compare this method with Hanama. And it is not difficult to find this expression that you see here in 21, which is the same than before, but now we have this extra prefactor here. And then from this mode expansion with splitted points, we can perform the adiabatic expansion. This is the adiabatic expansion, the same than before, and now we have this extra factor here. And this extra factor here is very meaningful, no? Because now what happens with this extra factor is that it makes the integrals convergent. Okay, so we had before these divergent integrals, and now we have convergent integrals. So it is a big difference, no? For example, if we integrate the leading order, we find this function here, which is the k Bessel function of order 0, okay? This is an example. So now I have introduced again the adiabatic method for charge scalar fields, and for 2 minutes, let us forget about adiabatic. Let us forget about cosmological backgrounds. Let us forget about the spatial point splitting, and I'm going to explain the very basics of the Hadamard regularization method. Okay, so in general, here the language is a bit different, but don't be afraid because I'm trying to show you as less formulas as possible. Okay. So when we are in general space-times, we in general don't have a lot of information about the quantum fields. We cannot do these mode expansions in general. We don't have an analog adiabatic expansion for other cases. However, we have some tools that allow us to have some general information about the main quantum objects, okay, that we have. In particular, what we have here and what is interesting here is that we have one tool which is called the Hadamard expansion of the Green function, which gives us the Feynman-Green function in terms of an expansion of the geodesic distance between the two split points that we are considering. Okay, so in 2 dimensions, the Hadamard expansion of the Green function is given by 25. So we can see here that we have 3 different functions in the expansion: this W, this B, and this logarithm. And what I claim here is that this Hadamard expansion is capturing all the possible short distance divergent behavior of the Green function. So you can see, well, I'm telling you that V and W are regular when sigma tends to 0, but of course this logarithmic term is divergent. Okay, so what this means is that the only potential divergency that we can have in the Feynman-Green functions in 2 dimensions is given by this logarithmic term, because this function V and this function W are regular. So it is capturing, in some sense, all the potential divergences that we are going to have in our physical observables, okay? So we, in general, don't have a lot of information about B, about sigma, about W in general space-times, but we can have some information about its short distance behavior because we can make Taylor expansions or series expansion of these functions, and we can get the first coefficients by iteration from the field equations, okay? So the important thing about 25 is that it is capturing the potential short distance divergent behavior of the Green's function, okay? I'm going to jump to the next slide. Okay, so how do we compute the normalized quantities? With this scheme, it becomes straightforward. What we have to do is to subtract to the full Feynman-Green function the divergent part, which in this case together, so we can compute the vacuum expectation values at coincidence. Okay, this is some general behavior that we have, but the problem is that for particular spacetimes, in general, we don't have any clue about the form of the functions that we are using here. We don't know we don't have close expressions for V, we don't have close expressions for W, we don't have close expressions for sigma. So it's a bit like, it could be understood more like a general rule than a particular recipe. But the good thing, and what is interesting with this method, is that we don't need the full expression of our functions. We only need the short distance behavior. And we can have it from the series expansion or Taylor expansion that can be done of our functions. Okay, so I'm going to show you the particular expansions that we can do for Friedman-Robertson-Walker universes and for spatial splitting and including the electric field, and then we will be able to compare it with adiabatic. It will be fast. Okay, so as I said, we don't have close expressions for the geodesic distance, for the V and for the W, but we have the short distance expansion. In particular, for spatial splitting distances, for short distance, it is not difficult to see that in Friedman-Robertson-Walker universes, the geodesic distance goes as you can see here. We can also find the short distance behavior of the scalar B that I recall you that is the term that is multiplying the divergent part of the Green function. And I want to recall also that the form of this B is completely determined by the background, which is by the space-time, by the geometry, and also by the electric background, which means that the divergences are not related with the quantum state. Okay, so after some algebra and using some formulas that I'm not showing you here, we can find the short distance behavior of the divergent term, which is this. Okay, so we have the logarithm and we have this this expansion. Okay, so now if the adiabatic regularization procedure is consistent, which means that if the adiabatic regularization method has the same encapsulates the same divergences than this method, we have to be able to reproduce this behavior. Okay, so this is a summary. From the Hadamard expansion, we can find the divergent part of the Feynman-Green function, at least for short distances, which is this one. And I claim that for adiabatic, we can do the same. How can we do this? Because we know how to split the points, we know how to compute the adiabatic expansions, and we realize that this term here makes the integral convergent. So it means that we can perform the integral, then to do this short distance expansion, and we should be able to get something similar to the expression that you see here. Okay, so let's do this. Before I showed you that the integral, this particular integral of the leading order gives us this result in terms of the Bessel 0K function, okay? And this function can be easily expanded around 0. It has this behavior, and it is important to recall that we have to include also not only the leading order, but also this next to leading order. So we did this for the adiabatic order 0, and we have to repeat this for the adiabatic order 1 and for the adiabatic order 2. And after this, and after do the full integral, we have to study the short distance behavior. So it is important to do the full integral and then to study the full short distance behavior, because as you can see in 29, the leading adiabatic order is giving leading and next to leading short distance orders. Okay, so now let's compare the leading order in the short distance expansion for Hadamard with the leading order in adiabatic. We easily find the following. In Hadamard, since this is like the minimal prescription, it's giving only the divergent terms, we find this term here. While in adiabatic, we find a logarithmic term, a logarithmic divergency, and then we find these finite terms here. Okay, so only from the leading order we can extract some conclusions. Then, first of all, one thing that I forget is that the Hadamard method includes an ambiguity in its definition. Okay, because we want the argument of the logarithm to be adimensional, we have to include this length scale, which is arbitrary. In the adiabatic, I said that the method is unique. So when we do this short distance expansion, we see that it naturally gives us a scale. Okay, so comparing both expressions, we see that the adiabatic method fixes the arbitrary length scale Hadamard to a one particular choice. Okay, and then we also see that the adiabatic expansion includes some finite terms. Which is fine, because the minimum requirement is that the adiabatic has to capture the diverging behavior. Then the finite terms are fine. Okay, so this I showed you this for the leading order in short distances, but if we repeat the same in the next to leading order and next to leading order to x squared order, we find that the divergences are completely cancelled. Okay, so we end up with a finite result, which means that the adiabatic method is consistent because it's capturing the same divergences that Hadamard, which gives us a rule for the general divergences that they have to appear. Okay, so in summary, the conclusion that we can extract from this analysis is that the adiabatic expansion can be understood as a particular choice of Hadamard. Why? It can be understood like this because it gives a natural scale, so it's fixing the Hadamard scale to this particular scale, and then because it also includes some finite terms that can be interpreted as a choice of omega, that can be absorbed in the omega part. If you remember the Hadamard expansion, we have the b and the logarithm, and then plus this finite omega b scalar. So we can reabsorb these finite terms into this omega. So it can be interpreted as a particular choice of the quantum state. Then regarding with renormalization, the conclusion is that the adiabatic regularization method is valid because it is compatible with a general covariant method that eliminates the expected ultraviolet divergences. And then it arises some interesting question. That is that, as I said the adiabatic method is a non-minimal method because it's subtracting the ultraviolet divergences and other finite terms. So it means that after renormalization, the vacuum expectation value of the 2-point function is not the same in adiabatic than in Hadamard. So a natural question is, can you change the physics of the problem? Which method is the right method? Which method is describing as the reality? No? So that's all. In summary, we have analyzed the ultraviolet behavior of the 2-point function via adiabatic regularization and via Hadamard point splitting, and we have tried to compare the two methods, and the conclusion is that they are compatible and that the adiabatic expansion can be regarded as a particular choice of Hadamard. But it is true that in terms of renormalization, we are subtracting different terms. So we can have potential physical differences. And the last thing is that I show you the results in 2 dimensions, but we expect to extend them to 3 and 4 dimensions. So that's all. Thanks for your attention. I hope you have enjoyed my talk, and I'm going to jump to this. If you have any question.
Question? We are okay. So
I can add something that I wanted to ask you, Silvia. I'm Santi, by the way.
Hola.
Do you know if there is a relation between the Hadamard method and the Bitterswinger expansion, which we usually use?
Yeah,
general,
Hadamard and adiabatic are the same, no? Sorry, the Bitterswinger and the adiabatic are the same in this sense. So they are not non-minimal and they are subtracting the same omega. So the Bitterswinger can be also regarded as a particular choice of Hadamard, which is subtracting the minimal divergences and then these finite terms. So we can say that the Bitterswinger and adiabatic are the same, but the Bitterswinger is more general because it can be applied to other spacetimes. But the Bitterswinger is a particular choice of Hadamard that eliminates the divergences and then these extra finite terms.
Okay, thank you. Very clear.
okay. Any further question? No? Okay.
Sorry. Hello. Can you hear me?
Yes.
Okay. I just have a little comment, Silvia. If you maybe can comment on that. I recall that there is a discrepancy in the trace anomaly for the electromagnetic stress energy tensor in 3+1 dimensions. A discrepancy in one of the coefficients of the trace anomaly. You know that it is an expression that goes with Biles, Riches, and there's a term that is a box of R. The quotient that goes with that box of R is predicted to be 0 using dimensional regularization, but point splitting methods give a different value for that coefficient. I don't know if you knew that, but I saw it in a paper by Elizabeth. So maybe you can.
I can ask her.
Okay, because there's, it's puzzling for me that they give this discrepancy.
No. So in that case, it can be this thing that can be understood as a preferred choice, no, for the subtractions, no, like maybe Hadamard is not enough and we had to subtract something more or something like this.
Yeah, it looks like maybe dimensional regularization is, as you have shown here, like a particular choice of the Hadamard expansion. I don't know, but I just wanted to throw that.
Okay, thank you.
Thanks for the talk.
Thank you.
Okay. I think we finished. So let's thank again Silvia.
Thank you.
So it's time to say thank you everyone, all the speakers and all the attendees. So, yes, and everyone at home or online, wherever you are. Thanks a lot for your talks, your comments, your questions, your participation. I think it's been a very interesting and diverse meeting, and we hope to
have your company again in the future in other meetings. Particularly next month, we will have the 5th edition of the Valencia Winter Workshop in autumn, but it's winter. And we hope that you will join us and participate again in that event. So thank you so much to our special guest, Fabio Morati, who is waiting to take his plane in just a few minutes. Adiabatic, thank you so much. And Álvaro de la Cruz, don't breathe, for being the guilty of this event and others previously. So thank you so much to everyone. And goodbye.